This is the last part of the stoichiometry chapter. We're going to cover limiting reagent and percent yield today. So there are three types of problems in this chapter. We've gone over the two-step problems. And remember, the two-step problems, they could be mole-mole or mole-gram or gram-liter, any combination of those. And we've covered those. We're going to go on to limiting reagent today and percent yield. The limiting reagent problems, we're going to use the example of this chair for now, and there's two parts. There's the plastic seat and there's four legs. And so far on the problems, they've given you one part, one reactant, and they just assume that we're not going to worry about the other one because we had plenty of it. Some of the problems will say that the other reactant is there in excess. So let's say we had 1,000 of these plastic parts and 8 legs. When we were trying to put this chair together, the problem so far would just say, we have 8 legs, how many chairs can we build? Well, that would be 2 chairs because there's 4 legs in each chair. We don't worry about the plastic part. They're just assuming we have plenty. Well, in limiting reagent problems, they're going to give you how many plastic parts we have and how many legs, and they're going to ask you, figure both of those and come up with an answer for how many chairs we're going to make. So, how do we know when we have a limiting reagent problem? They're going to give you 2 reactant amounts. So there's basically going to be 2 knowns. There are a couple of terms that we need to be familiar with when we're talking about the limiting reagent problems. One of them is limiting reactant. That would be the part we run out of. In that example, the 8 legs, well, we made 2 chairs and we're out. We can't make any more chairs, even though we have 1,000 of the plastic parts. The thing we run out of is the limiting reactant. The part we have extra, that would be the excess reagent. So, and at the bottom of the PowerPoint page, it says to solve these, you're going to solve both knowns for product. If there are 2 products, it doesn't matter which one you solve for. You could solve for either one. But remember, in most of the problems, they're going to ask you how much product is produced. They will specify which product. So if they tell you in this example, let's say that we had water and CO2, it was a combustion, and they said how much CO2 is produced, well, there you go, solve for CO2. But if they're just asking for the limiting reagent, you could solve for either product. So we're going to move on to an actual problem. We're going to use the combustion of hydrogen. 2H2 plus O2 yields 2H2O. And the combustion of hydrogen, nice simple little problem. Everything's easy to add up, so it should be a fairly easy example. Now, here's the problem. They say, given the above reaction, when 6 moles of hydrogen react with 2.8 moles of oxygen, you should see right away we have 2 knowns. So we have a limiting reagent problem. How do we solve it? Well, we're going to set it up and solve both of the knowns for H2O, for product. So we have 6.0 moles of H2. Draw 2 blanks. Here's our known. We're going to cover the number, drag the units down, moles of H2. And we're going to solve for moles H2O. Okay, so where do we get the values for our conversion factor in stoichiometry? The balanced equation. H2O, value is 2. H2, value is also 2. It doesn't always come out the same, it just happened to be here. 2 over 2 is 1, so 6 times 1 equals 6 moles of water. Now, if it were an old problem, one that we're given one known, we could stop there and say, all right, we're done. But on this one, we actually have to solve the other part now. So we're going to look at the other reactant, which is O2. We have 2.8 moles of O2. Cover the number, drag moles of O2 down on the bottom, and there's 1 mole of O2, and there's 2 moles of H2O. So we have 2 answers now. 2.8 times 2 equals 5.6 moles of H2O. Now, how do we get our answer from all of this? Well, so the way to do that is to look at the two answers. One of them says we can make 6 moles. The other says we can only make 5.6. The low number, that's the winner. And we're going to scratch through the other one because it's not ever going to be useful to us, since it's like with the chairs. Once we've made 2 chairs, we're out of legs. We're not going to make any more chairs. Even though we have 998 of those plastic tops left, we're not going to make any more chairs, so that's useless. What are our answers? Well, there's 3 things that are going to be asked. A, what's the limiting reactant? That would be O2. O2 is the limiting reactant. Second, how much product? Well, the winning equation, the low one, it's kind of like golf score, the low one wins. This would be the answer to B, is 5.6 moles of H2O. So we've got 2 of our answers. The third answer, the third question is how much excess is left over. And the key to that is make sure you don't just subtract your 2 values for water. We're not looking at water now. We're actually trying to figure out how much H2, the other reactant. Here's our limiting reagent. We want to figure how much H2 is left over. And the way to do that is, and this is important, this third step, if you follow these steps, you're going to do well on this part C. It is to take your winning equation, this bottom one, 2.8 moles of O2 over 1. We're going to cover the number, drag the units down again, just like we did there, and we have 1 mole of O2. But instead of solving for water, we're going to solve for the other reactant. We want to find out how much of the excess was used. So we're solving for H2 in this case. So we put moles of H2, and there are 2 moles of H2. Now, when we multiply this, we get 5.6 moles of H2, and I don't want you to think, oh, well, that was the same as this. It just happened to be the same in this problem because H has a 2 in front, H2O has a 2 in front, and that's just an accident. Some problems have the same, some don't. So make sure that you do the right steps for this third one. Take the winning equation, solve for the other reactant, in this case, 5.6. How much were we given? We were given 6 moles, and we used 5.6. Subtract that. You've got your how much excess is left over. So we have 0.4 moles of H2 is left over. That's our answer for question C. So we're going to move on and talk about the last type of problem. The last type of problem is the percent yield problem. The percent yield problem, it's easy to identify when we're doing percent yield because it'll actually say what is the percent yield. So that's a little flag that goes up, and you know right away that that's the type of reaction that you're going to be doing. So we'll move on the PowerPoint, look at the last couple of pages. For percent yield, the steps are at the bottom. The first thing it tells you is when you see percent yield, you're going to write percent yield equals actual yield over theoretical yield times 100. Make sure that you write that first step because this is your template for how you're going to solve the problem. Second step, we're going to go in and find the 2 numbers. There's always going to be a product value in grams and a reactant value in grams. And the product number, this is real important, and if you look at the last page of that second day notes, here's our problem. It says, what is the percent yield of the following reaction? I'm going to write the reaction up here. And that reaction is CaCO3 decomposes with heat to give CaO plus CO2. You should recognize this as one we did back in chapter 8 and 9, decomposition of carbonate. And there are 2 numbers they give you in the problem. It says we have 60 grams of CaCO3, okay, 60.0 grams of this, and that we have produced 15.0 grams of CaO. The key there is there's a reactant amount and a product amount. You need to find the product amount first. We're going to write that on the top blank of our equation. The 15 grams will go right here. 15 grams CaO. We erase this bottom and we're going to write grams of CaO here. If you've ever heard the adage about you don't compare apples and oranges, compare apples and apples, that's what we're doing. We're comparing grams of calcium oxide to grams of calcium oxide. So that's the first of the two numbers. The second number you're given will be a reactant amount, and a theoretical value is a calculated value. Actual is what we produce in the lab. So we've already got the actual. This is what we made in the lab. We want to find out what we should have made. So your lab partner spills a little bit, doesn't measure right, something goes wrong. You're not going to make 100%. We're always going to have some amount that's less. And this bottom number is the calculated value. So how do we get it? We calculate it. We start with the reactant amount, which is 60.0 grams of CaCO3. And we're going to do a two-step problem, and the answer will go into the bottom blank. We're going to calculate how many grams of CaO we should have produced. So, just like before, we covered the number, drag the units down, grams CaCO3, and how do we get mole to mass? We add up on the periodic table the parts. We've got Ca, which is 40.1 grams. We've got C, which is 12.0 grams. And we've got O3, which is 48.0 grams. Remember, we got all those from the periodic table, the gram atomic mass under the symbol. When we add that up, we get 100.1 grams, and that's how much CaCO3, 100.1. Draw a bubble around CaCO3, and we weighed the bubble. Ca, C, and O3 all add up to 100.1 grams. Well, that is what goes from the balanced equation. That goes down here on the denominator. We also need to know how many grams of CaO. Draw a bubble, and we weigh that. Well, we've only got two parts to that, and that would be 40.1 plus 16. Oxygen is 16, calcium is 40.1. When we add those up, we get 56.1 grams. The 56.1 grams goes in the top blank because 56.1 grams is our balanced equation amount of mass for calcium oxide. At this point, we solve it. 60 times 56.1 divided by 100.1. And when we do that, I think we get 33.6. Punch it real quick. 60 times 56.1 divided by 100.1, it's 33.6. And that's how many grams of CaO we should have made. Remember, in the lab we don't make 100%, but this is what we could have made if we made 100%. That goes on the bottom. And now we've got 15.0 divided by 33.6 times 100. And when we process all that, we should get 44.3% yield. Just run that through to make sure we've got it right. So 15 divided by 33.6, 44.6% yield. So we rounded to three significant figures because we have 3 on both of those numbers. That percent, it's a low percent. It's usually going to come out higher than that. Usually do a little bit better in the lab, usually somewhere between 80 and 95%. But this particular problem, maybe your lab partner spilled a little extra, didn't turn the heat up the right way. And we ended up with 44.6%. So just to kind of recap on this, remember in this chapter we've got 3 main types of problems. We've got the two-step problems that we worked on in the last session. We have limiting reagent problem. How do we know a limiting reagent? When we are giving 2 known amounts for reactants. and it will also usually say what's the limiting reagent. The third type is percent yield. It'll say percent yield, and then you write your equation: percent equals actual yield over the theoretical yield times 100. There are lots of practice problems for all of these. You've got your review to work on. Try to pull all that together and do lots of problems. That's how you get better at this. Good luck.